Yes, here we are. It's the physics video lecture. Physics 107B, video lecture 13. Okay, today we're talking about electromagnetic waves again, this time in conductors. And we'll set up Maxwell's equations, a little preliminary stuff, and then solve them again. Some interesting results. Okay. Good, so electromagnetic waves in conductors. Yeah, so what's different here is that we have free charge. So divergence of E, unlike in the vacuum, not vanishing, so we have free charge over epsilon. Divergence of B, of course, vanishes. We have Faraday, curl of E. And ampere, curl of B, u epsilon, E dt. But now we have some current density, so we're going to have a J right here. However, the free current density is given to us by Ohm's law. Okay, conductivity times E. So that's what we're going to substitute here. So instead of the J, we're immediately going to have plus U sigma times E. So those are the Maxwell's equations. That we're going to use with, but first we're going to talk about the continuity equation. We also have a continuity equation for the free charge, and that would be d rho sub free dt plus divergence of j sub free is equal to 0. But now with Ohm's law, we can write time derivative free charge plus sigma divergence of E is equal to 0. But we have something for the divergence of E. So once more, sigma, and then, in fact, Noah, let's go ahead and bring it to the other side already. So that's going to be equal to minus, and we've got that sigma, we've got rho over epsilon here, so E rho, and there's a differential equation to make that look a little more natural. Minus sign. So that thing has, this is free, a basic decreasing, decaying exponential in time. So we can write this down immediately. So we have density as a function of time, got an initial condition, and e to the minus sigma over et. Okay, so there's an inverse time right there, and if time is sufficiently great compared to that inverse time, then this is exponentially crushed. It goes to 0, greater than or equal to 1. Okay, and we can express this in terms of a frequency as well. Okay, if there's a time scale, then a frequency is just the inverse of that time scale. Which is to say, if omega is much less than the sigma over epsilon, we also have this condition fulfilled. And the omega will come into play when we set up our wave equation. So what we have is, we're going to substitute a 0 right here in our Maxwell's equations. I'm not going to write them down again. Here, I'll just we have divergence of E equals 0 under these conditions right here. That's a transient that decays. Okay, but having these conditions again makes these equations very nice to solve. Good, so that's our next step. Actually, our next step is to take these 4 equations, this one, these 3, and extract the wave equations. So you probably remember how we got the wave equations. We took the curl of both of these equations. In fact, we're going to see we get the same thing for E and B, the same differential equation. So let's go ahead and start with the electric field. Take the curl of the curl of E equal to minus d over dt curl of B. Okay. So yeah, we plug this curl of B in down here. It's going to go in here. Here we have an identity, grad divergence of E minus del squared of E. So yeah, that's why we needed that divergence of E vanishing. We're going to just get rid of that term again. Here we're going to have minus time derivative of this curl of B here. So we'll be able to pull mu epsilon, we'll have d squared E dt squared. This one's also going to be in here. So mu sigma times, and since it's a time derivative, so minus mu sigma dE dt. Okay. And yeah, one more step, we'll just get rid of all these minus signs. We've got del squared E equals mu epsilon d squared E dt squared mu sigma dt. That's one of our differential equations, one of our wave equations, and it has the look of that damped wave equation that we get with that wave on a string in a viscous fluid problem from the homework. Same form, 2 derivative, 1 derivative, should be a plus sign here. Yeah. Okay, the same thing happens with B. So the left side here, we're going to have well, let's go ahead and curl of B equals not just mu d dt curl of E plus mu sigma curl of E, and then we substitute from the other equation. First of all, on the left side, once again, if B, that one vanishes, no, minus del squared B, and on the right hand side, mu epsilon, time derivative of the curl of E, there's our minus dB dt, so minus d squared B dt squared plus mu sigma curl of E, again, minus dB dt. So you get one, you get the other one, and they have exactly the same form. Okay, so del squared B is equal to U epsilon 2 time derivatives U sigma dB dt. Okay, so exactly the same. So we're going to solve for one of these, doesn't matter which one, solve for this one here. And later when we want to find out about B, we'll be able to use this condition here. Actually, these three will go back into the Maxwell equations and find the relation between these two fields, okay? Which is very similar to what we had before. Okay, let's go ahead and set up and solve this. Yeah, these first derivative terms, they add some algebraic complication, but interesting points to the whole mix here. So what we're going to do is go ahead and say E is going to propagate in the positive x direction. It's going to be a plane wave ansatz as before. So E0 e to the I k tilde z minus omega t. Okay. So we could think that k tilde is real, but we'll find out as soon as we go into this differential equation that it's complex. Okay, we're taking omega as a real frequency. So we just go into here and see what happens. So on the left side, we're going to have two derivatives with respect to z. We're going to have I k tilde squared. On the right side, we're going to have U epsilon, two derivatives with respect to time, so minus I omega, also squared, U sigma, one derivative with respect to time brings down minus I omega. Okay. So this is why you see this is real, this is imaginary, this is a number squared, complex number squared. The complex number k tilde has to have a real and an imaginary part. So let's do this. So we have minus k tilde squared U epsilon minus omega squared minus I mu sigma omega. So the minus signs go away. But again, real, imaginary, so that's got to be the following. What we're going to do is let k tilde be a real part plus an imaginary part. So it's a real k and it's imaginary kappa. Okay, imaginary, yeah, kappa. So when you square this, you get k squared minus kappa squared for your real part. Kappa. Draw our kappa here. K squared minus kappa squared. And that's going to be this mu epsilon omega squared. And for the imaginary part, when we square this, we get 2I kappa k. We're going to have 2k kappa is going to be equal to mu sigma omega. Okay, so those are two equations and two unknowns because we want to get k and kappa in terms of all these constants and the frequency. So algebraically, we plug one into the other. So we're going to have k squared minus, now that kappa is mu mu sigma omega over 2 squared, and then 1 over k squared going to be equal to mu epsilon omega. And what we do is multiply through by k squared. Bring this to the left side. Let's see what we get. K to the 4th minus mu epsilon omega k squared minus mu sigma omega over 2 quantity squared equals 0. Let's see how we're doing here. Sigma omega over 2 squared. Yes. Good. So now we're going to solve this coordinate for k squared. As luck would have it, k squared equal to 1/2, so negative b, so mu epsilon omega plus minus the square root of mu epsilon omega squared. Minus a negative is a 4, but that 4 is going to cancel the 2 squared, which is 4 right here. So plus mu sigma omega quantity squared. Actually, I'm missing a squared here somewhere. Let's see. Squared. Epsilon omega squared. Should be right here. Yeah, mu epsilon omega squared. There we go. That's better. Okay, we'll do one simplification. So we want to take the whole square root of this. And we can see we've got mu epsilon omega squared. We can pull that out. So we're going to end up with k equals mu epsilon root got an omega times 1. Get a 1 here as well, and then we only have an omega squared here, so we multiply top and bottom by omega squared, so we end up with, and then mu cancels, so we end up with sigma over epsilon. Let's see, sigma over epsilon omega. And you can see the relation. There's a relation between sigma and over epsilon and omega, as we saw earlier. Okay, that kind of controls the behavior of this thing here. So close parentheses, and got the square root out here. So this is also a 1/2 power. So there is k. Now, kappa, you've got a little trick here. Do I have that inverse? Yeah, so kappa is proportional to 1 over k. So you can actually make the substitutions over here, and you're going to have your kappa squared up there, and your 1 over kappa squared from this one here. Okay. So everything actually gets the same prefactors, except they've been switched. So what we end up with, same root mu epsilon over 2 omega minus 1 plus sigma squared to the 1/2. Is that enough? Actually, I should say that the k got the plus sign, and this one also has to have a plus sign. Yeah, so the plus sign was clear, because k and kappa are real, right? They're real and imaginary parts, so they're real, and we had to have the plus sign here. Minus sign would have made this imaginary again. Good, and this is greater than 1, so this is also correct. Okay, so with those, so very similar. We can now go back into Maxwell's equations. I can erase a bunch of this stuff. Good, so we're going to use these. We have our ansatz somewhere up there. But yeah, we basically know what's going on here. It just took a bit to get these expressions, k and kappa, right? They're kind of complicated. You can see the dependence on the frequency there, which is important. It's already been mentioned. But when we go in here, we see the kappa is giving us the damping, and otherwise the real part there is going to give us your standard behavior. And in fact, we see it's linearly proportional to omega as we expect it to be. So let's go ahead and go back into Maxwell's equations to tease out the behavior of these. Okay, let's see where we go here next. Good. So we'll just write down E and B as we now have them. E0, this is going to be the same argument we've done before. E to the I, but go ahead and write the K plus kappa Z minus omega T. So we got the same thing. But let's go ahead and draw this conclusion. So that was K plus I kappa, so we've got E to the minus kappa Z. So E0, E to the minus kappa Z, E to the I, KZ minus omega T. And obviously the same thing for B. So the relation of E and B comes from going back into Maxwell's equations. Minus kappa Z, E to the I, KZ minus omega T. first of all, drawing attention to it now, we have this e to the minus kappa z attenuation. And this kappa defines a depth called the skin depth. So d equals 1 over kappa skin depth, at which point it's, 1 e folding. And lambda, k, the same thing, k lambda over 2 pi. I'm sorry, k 2 pi over lambda, same as before. But so now we take these equations, and actually we'll go ahead and take this form into Maxwell's equation. Okay. So what happens? We're supposed to have divergence of E vanishes. Now there is no y, there's no x and y dependence, so it's only the z component. So we're going to have divergence of E equaling 0, telling us that d dz E sub z is equal to 0, but we have I k tilde tilde well, k tilde is not 0, E sub z has to be 0, so we again find transverse waves. Okay, so I hadn't drawn it, but let's go ahead and do a little drawing right here. We've got our x, y, z, we're propagating in z direction. So the transverse wave, we could go ahead and let E be polarized in the xz plane. Okay. E sub z equals 0. And the same for B. Of course, E sub z is also equal to 0. Good, so we have that. Then we'll take Faraday's law. Curl of E equals minus dB dt. So let me go ahead and send this up. So next, curl of E equals minus dB dt. Okay. So what's the curl of E going to be? We're choosing this polarization. Let E equal, EX x hat. So if we do the curl of E, we have we start this one off with okay, x hat, so dy dz minus d dz dy x hat d dz dx minus d dx dz y hat plus z hat. So there's the curl, and these all just go away one by one. Okay, we have our ex, but there's no y dependence. We have no ey. Ex z dependence is the only one that survives. We have no ez. Ey with respect to z, none. Ez with respect to y, also none. Okay. So this is the only one that survives. So we end up with minus d ex Z y hat, and that's equal to minus dv dt. So here, the derivative with respect to z brings down our k tilde. So we have I k tilde, so minus I k tilde ex equals minus, and the b, of course, we're just bringing down a minus negative I omega. Negative I omega b. And that gives us the relation between b and e. Okay. This was y hat. So the polarization of B is in the y direction on my little picture there, just as it was before. The only difference we're going to find is a phase lag. So let's wrap it up with that. So I k tilde ex y hat minus I omega b hat. Good. So finally, yeah, go ahead and set this up. Okay, so up until now, up to the attenuation, nothing has really changed from our previous picture. Okay, so we have x, y, z. I'm only going to draw the E field right now. Okay. There's our E field. But this equation here is with complex. And right, if you strike the I and minus signs, you still have a complex number there, which means there's a phase shift built in. So we can look at this k tilde. So k tilde equals k plus I kappa in the complex plane, and then we'll have. We can imagine we've got K, an angle kappa, so K plus I kappa, that's that point here, we'll call this capital K. And this is going to be the phase shift between if we had just had a real K as opposed to this complex one. Or K tilde is equal to K e to the I phi. And therefore we're going to add a phase shift. Phase shift between, no longer up here, between the E field and the B field. Okay. So there's a phase shift, they're no longer in phase here. Okay, they're going to be out of phase a bit. We'll have a phi right there. Okay. Good. So what we're going to do, I had a couple of more homework problems that I'm going to list. I'll put these up while I'm still on the subject. So these are the remaining problems from chapter 9. 21, 27, 30, 39, and 40. And a couple of these will be dealing with the material we just covered, and a couple of them will deal with next lecture, which will be on waves and waveguides. So next, waveguides. Okay, we'll leave it at that. See you guys next time.